Hello, today we're going to cover the photoelectric effect and we're going to understand how it shows the particle nature of light. I'm going to make this video extremely easy to understand, and at the end of the video I'm going to give you two tips that if you use them, you'll be able to apply this to any question and be able to understand the photoelectric effect very easily. So the photoelectric effect in basic is when you shine light onto a metal surface, you get electrons being emitted. This light needs to be above a certain frequency, and the electrons emitted are called photoelectrons. To understand why it shows the particle nature of light, first we need to understand wave theory. Wave theory tells us that the energy of a wave is proportional to the intensity of light, and that waves spread out evenly. We know these two things, so now let's apply this to the photoelectric effect. If light were to be a wave, it would have a wavefront like this and would spread out evenly. And each electron on the metal surface here would gain equal amounts of energy. This shows the energy. And if you were to increase the amplitude of the wave, so increase the intensity of the light, I'm drawing the waves thicker now, the electrons would have a high enough energy now to leave the metal surface. However, what we see in the real photoelectric effect is that the kinetic energy of the electrons is independent of the intensity of light. Now, I'm going to introduce Einstein's photon model of light. This idea is that electromagnetic waves exist in discrete packets called photons. Here, a wave is actually made of smaller packets like this. This is just a representation of what you can imagine it to be. And now, these photons can have one-to-one interactions with the electrons, particle to particle. For example, as I have drawn, once this electron has had an interaction with one photon, it has enough energy to move and does not interact with the rest of the photons. If it isn't released, it loses all its energy before another photon can interact with it. This is just an oversimplification, so it can be easier to understand. So now, let's look at what happens when a photon hits an electron. The energy of a photon is described as hf, where this is the frequency and this is Planck's constant. Bear with this at the moment, and it might look a bit complicated, but we are going to simplify this later on. So now, if we look at the conservation of energy, let's make an equation for what happens between a photon and an electron. We know that the conservation of energy is energy before is equal to energy after, and the energy before in this one-to-one interaction is just the energy of the photon, because we can just assume the electron's energy is negligible as zero. So the energy before is just hf, which is Planck's constant, times the frequency of the photon. Now we need to look at the energy after, and the energy after is the kinetic energy of the photon here, so ek, and also plus the energy needed for the electron to escape the metal surface. Let's first explain what this energy is. The one for the electron to leave the metal surface. Let me explain this briefly. If you did GCSE chemistry, you would know that electrons exist in energy levels in the atom. So the energy for an electron to leave the metal surface is like the energy the electron needs to escape the orbit of the atom. This is oversimplified but will help you understand this. Now, we would know that the electrons at the highest energy levels would require the least energy to escape the metal surface. Now we know that the total energy is split into two: the kinetic energy of the electron and the energy needed to escape the energy levels of the atom in the metal surface. The electrons with the least energy needed to leave the metal surface would take a larger share of the total energy for their kinetic energy. So they will they will have the greatest kinetic energy because they have more energy left over from HF that is converted into kinetic energy, and used to gain speed. These electrons need the least amount of energy to leave the metal surface, and are also electrons that will have the largest kinetic energy. So now we've made an equation from the conservation of energy for the electrons that need the smallest amount of energy to be released. Therefore, Therefore, this would also mean that they require the minimum amount of energy to be released, and this would be the same minimum amount of energy for any electron to be released, as these require the least amount of energy out of all the electrons. So for this equation, we have the energy before and the energy after. Before, we only have the energy of the photon, and after we have the kinetic energy of these electrons, which is the most kinetic energy any electron can have because they take the most share of hf towards their kinetic energy. And here we also added the energy needed to release these electrons from the metal surface. And this is given by a Greek letter called phi, and it's called the work function. This is basically the energy needed for electrons for the electrons with the smallest energy to be emitted, and therefore the minimum energy for any electron to be emitted. It is measured in joules because it is an energy in this equation, and this depends on the material of the surface, and different types of materials have different work functions. This is because it takes different amounts of energies for the electrons at the highest energy levels to be released. Now let's find the minimum frequency needed for the light shone onto the surface for electrons to be emitted from the surface. We would use all of our energy from the photons just to release the electrons with the least amount of energies needed to be emitted, so no energy would be left after for the electron. Using the same equation and substitute Ek max as 0, as there is none, as we are using all the energy to release the electrons at the highest energy levels. So now we will have an equation HF, but now F is the minimum frequency to release electrons. Let's call this F naught, and this is all equal to the work function. To find this frequency, we just rearrange, dividing by Planck's constant on both sides, and we get this equation here. The work function of a constant is equal to the minimum frequency needed for electrons to be emitted. Now let's plot the maximum kinetic energy for the electrons emitted against the frequency of the light that we shine onto the metal. We just use this equation and rearrange it in the form y equals mx plus c to make a straight line equation to plot on here. The y-axis is the maximum kinetic energy of electrons released, and the x-axis is the frequency of the frequency of the light. So now, if you rearrange this equation to make y the subject, take away phi from both sides, you will be left with hf minus phi is equal to ek max. Now let's make this look a bit better. Ek max is equal to hf minus phi. So what do we know from the straight line equation? M is the gradient and c is the y-intercept. If we compare the coefficients of these two equations, this is y and this is x. And what we see is that the gradient is Planck's constant and the y-intercept is the negative of the work function. Okay, so now we plot this onto the graph. We know that the y-intercept would be the negative of the work function. We know that the gradient is Planck's constant, but that doesn't really matter here as there is no scale on our graph. Now let's find the x-intercept. To find the x-intercept, we would substitute y as 0. And what is y? Ek max. Ek max is 0. And what did we say when Ek max is 0? We see that the frequency is equal to the minimum frequency needed for electrons to be emitted from the metal surface. So this makes this so simple. We know now that the x-intercept is f naught, or the minimum frequency needed for electrons to be released. Now we have 2 points on the graph, we can just connect them to draw a straight line. However, this is what might make it a bit confusing. Kinetic energy can't really be negative, so what the graph actually does is follows the same trend on this side here, but when it reaches below F0, no more electrons are released. So below this minimum frequency, no more electrons are emitted, so we can just say that the kinetic energy of these electrons are zero because they have not been released. To recap what we've done so far, you can understand everything we've done just using the equation of conservation of energy. HF is equal to EK max plus the work function. You can apply this to the graph, you can apply this to the minimum frequency needed for the photoelectric effect, and everything we've covered so far. You will be able to understand it using just this equation. This is a key equation and you should practice it a lot so you can remember this equation and understand this a lot clearer. This is my first tip for today that I'm going to give you. Now, you might have heard that you need to learn something called stopping potential for your A-level specification. This might seem a bit complicated at start, but we're going to make it simple for you to understand. Now, let's imagine we have a metal surface like before, and let's put it in a vacuum, just to make sure there's no air molecules bumping around with the electrons while they're being emitted. And we will connect this metal to a battery and put it on the positive terminal. And the other side we will connect it to a negative electrode called an anode. Now we can apply a voltage with this battery, so the metal surface is positively charged. We are going to do the same thing and shine light onto it, like in the photoelectric effect from before. What would you expect to happen when we shine light at a high enough frequency for photoelectrons to be emitted? We know that like charges repel. This is an electron, for example. A negative charge repels a negative charge. And we know that opposite charges attract. So a negative charge and another electron attracts to a positive charge. If we have electrons being emitted from here, let's draw another one, we would expect them to, even the ones here, even the ones still on the metal surface, we would expect them to all feel a force in that direction because these are all negative and they are attracted to the positive side and are repelled by the negative side, so they would feel a force in this direction. This is when we are applying a potential difference between the two plates using the battery from before. Now, if we increase the potential difference high enough, the electrons would experience such a strong force towards the metal that they cannot escape the metal surface anymore. So what it would look like is as if there was no photoelectric effect anymore. This is when we increase the potential difference between the negative electrode, the anode, and the metal surface. Let's calculate how much potential difference is required for electrons to no longer be emitted from the photoelectric effect. The minimum potential difference required for this to happen is called the stopping potential. This potential difference must be large enough to even slow electrons with the highest kinetic energies to a stop, so that they are not emitted. So no other electrons are emitted either, as they would have less kinetic energies and wouldn't require as much potential energy to be stopped. So we can find this potential very easily by understanding the definition of potential difference. The potential difference is the amount of energy each unit charge has in a circuit, and it's measured in joules, the unit of energy, per coulomb, the unit of charge. If we put this into an equation, it is simply V, the potential difference, is equal to E, the total energy, divided by Q, the total charge. Looking at each electron, we would need an enough potential difference to slow it from the maximum kinetic energy to zero kinetic energy, so they are completely stopped. How much energy would you think we need to do this? We would just need the difference in energy between the maximum kinetic energy of the electrons and zero kinetic energy, which is just negative EK max, or the same energy that these electrons with the highest kinetic energies have. This is negative because we are applying this energy to slow them down. Looking at the equation from before, if we look at each electron, we can substitute the maximum kinetic energy as E, the energy, and we can substitute the charge as the charge of an electron because we are looking at each electron individually. The charge of an electron is known as E, which is 1.60 times 10 to the minus 19 coulombs, which should be given in the formula sheet in your exam. Substituting, we will get the minimum potential difference needed in this circuit, so no electrons are emitted by the photoelectric effect. V is equal to Ek max over the charge E. Looking at each electron separately, especially the ones with the highest kinetic energy, as they need the most potential difference to be stopped, because this is the minimum potential difference needed for electrons to no longer be emitted. So this is the stopping potential, and we can call it Vs. Now, we can just rearrange the equation to make it look nicely. By multiplying by the charge of the electron on both sides, EVS is equal to Ek max. Now I will leave you with two tips I have for this video. The first one is the conservation of energy equation, which you can use to understand everything about the photoelectric effect. So this equation here, which we mentioned before. And to understand the stopping potential, if you understand the definition of the potential difference itself, you will be able to understand the stopping potential clearly. So if you have watched this video and you have seen these two equations, you will be able to break down this topic and understand it a lot easier in the exam. This is my final tip, and I just wanted to mention that I do tutor online. If you found this video useful and want to cover more topics, you can send me an email through YouTube or in the link in the description, and we can sort out details for tutoring. Thanks for watching.